We have a couple of minutes. Any questions? Acetals, half acetals, cyanohydrins, hydrates. What's up?
Question about the NMRs in the lab. There was a fluorine F19 NMR in the lab. Are you going to go over that topic at all?
Fluorine NMR. I can see what type of questions you have, and I can make a few comments.
I'm just, my question is more general than specific. I'm not sure how to even begin interpreting it.
I'll go and do that now. Fluorine NMR is, well, it's in general just like proton NMR. Proton NMR, you look at the hydrogens in the compound. Carbon NMR, you're looking at the carbons in the compound. Fluorine NMR, you're looking at the fluorines in the compound. If the compound doesn't contain any fluorine, you will not have any signals in the fluorine NMR. One thing to keep in mind is that whenever you do IR, you scan a huge region of IR and you get all the peaks. In NMR, say the whole board is the NMR region. Okay? Well, proton may be here to here. Carbon may be here to here. Fluorine's actually close to proton. It's like here to here. But when you scan proton, you just scan here. When you scan fluorine, you just scan here. When you just now suppose there's some elements on the periodic table that they do overlap, and you might get two elements in the same NMR, but not your common ones. So that's one thing. Well, some of you everybody made a compound with like one fluorine. Okay, so one fluorine, you'd have one signal. Fluorine splits just like proton. Spin is 1/2. Neighboring fluorines would split a fluorine, but you only have one fluorine, so nobody's got a neighboring two fluorines next to each other. But protons can split fluorines. So if you got a compound that has a like a fluorine here, that's usually on this carbon, right? And then you have like a next door H, and then all these are like carbons, 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 carbons. This fluorine is going to be a singlet, doublet, triplet, what? Doublet. Be a doublet split by the H. So that would be a doublet. If you had one here, what would it be? If these are equivalent, it would be a triplet. If they're not equivalent, it would be a doublet of doublets. You may also get long-range splitting with fluorine. It's more possible to get long-range splitting that's beyond 3 sigma bonds. Basically, H's can't split your fluorine signal. And H is split just like H is always split. The spin is 1/2, so it's N+1. Every NMR is going to have you got to include some type of standard that you set at 0. For proton and carbon, you use TMS, tetramethylsilane. It has H's and carbons. But it don't contain any fluorine, so it ain't going to give a signal in the fluorine NMR. In fluorine NMR, is there a signal standard listed?
No, that was one of my concerns. As I was looking at the right-hand pane, I don't see any standards.
There's no standard.
Looked at this online, CL3.
That's expanded. Do you have one that's not expanded?
That's like a non-expanded, it's got it right there.
Yeah, there's a small, it's a 0.0003, it's basically 0. Something set at 0. Typical standard for fluorine NMR is hexafluorobenzene. All fluorines are the same. It only gives one signal. And that you set at 0. You can set anything at 0. I mean, you can make 0 any point you want. Now, one thing about the peak positions. In proton and carbon, it's sort of similar. You got your aromatic, you got your aliphatic region, and then the aromatic is downfield, and it's just 20 times the rule. Fluorine, no. Aromatics are actually more to the right, very often, I believe. So that can be very different. Did I answer enough?
I was just wondering, because the stuff that I looked up online said that one of the standards for fluorine was what, CFCl3?
Yeah, CFCl3. That's basically, if that was an H, that'd be chloroform. That's fluorochloroform. It's got one F, it's one signal. That's actually more common. I use this because this is a liquid stored in the refrigerator. This, I think, is pretty much almost a gas. And you have to get it in solution. You buy a solution of it. I've never used it. I use this. Now they give two different things. Thus, you got to say what is set at 0. In what I gave you, this is set at 0.
Okay.
Because this is actually like 150 ppm different than that. If you set this at 0, the thing about it is if you set this at 0, most of your signals are then negative.
Right, and that's what I was finding, so I couldn't make heads or tails
Yeah.
of this plot.
But if you set this at 0, then most of your signals are positive. Everything depends on what you set at 0. In proton and carbon, TMS is so universal, it's not even discussed. But in other things, there's more options, and you got to say, well, what's your standard? Yeah, hexafluorobenzene is the standard that I use. Okay. Let's get started. Acetals and hemiacetals. Now remember Beverly Hillbillies, up here, you got one. Oh. Swimming pools and movie stars? Well, this is acetals and hemiacetals and all that. Okay, acetal. Everybody knows what an acetal is. We forgot to mention, here we're using a diol to make an acetal instead of 2 equivalents of an alcohol. Why use a diol? Back over here we use 2 equivalents of like ethanol. How do we drive the equilibrium? One way to do it is to remove water. The problem with removing water is, which has a boiling point of 100, what's the problem? The ethanol, which boils at like 78, will boil out first. Okay, so you can't boil your water out. You'd have to remove it some other way. But if you use a diol, acid catalyst, you get this plus what? Water, right? If you start that oxygen, which oxygen started over here? That one, right? Here, boiling point of water is what? No tricks, 100. This here, though, it's a diol, and the boiling point is like 200 degrees because it's a diol. It's got lots of hydrogen bonding, okay? And so you can do your reaction at say like 120, and as the water forms, it'll come out as steam, boil over, but you won't lose your diol. So it's just about convenience in that manner. So that's one of the major reasons you make cyclic acetals. Just in practice, it's easier to use a diol. I know everybody was wondering about that over the break. Why diol? I just wanted to answer that real quick for you. Okay, let's get started here. Acetals as protecting groups. Here we saw it protecting the ketone. So we can then reduce the ester. And then we can, you've got it drawn in, and then we can deprotect. And so we went with acetal, we did the chemistry, and then we deprotected. With the acetal, went back to the ketones. Acetals can reverse back to the original, right? Run a Roman numeral 2, reversible, right? So that was protecting the ketone. Now you can also actually protect diols. And that's down here. So new stuff here, new stuff. Look at this. This is actually a diol. It's a diphenol. Reacted with magnesium. Maybe we're trying to make a Grignard here. Yeah? Problem is you can't make this Grignard. Or you can make it, but it's only going to exist for a fleeting instant. You can't make it and use it because as soon as this happens here, this is basically carbanion, right? Okay? Well, these are acidic H's. Just going to do a proton transfer. That is, this carbanion is going to take the acidic H of another molecule, and you're just going to put an H under carbanion. I mean, either that one can give it up or that one can give it up. It's just going to do that. So this is not a reasonable Grignard to make. You can't make Grignards in the presence of acidic H's or protic solvents or whatnot. Maybe you're trying to make this Grignard and react with the epoxide, you know, and get the carbanion to add and get the nucleophile carbon-carbon OH. That's not going to work. You can't do that chemistry with these protic acidic phenol groups. But it's a diol. What happens if we react this with maybe acetone and ACl catalyst? Well, just like up above, diol and aldehyde or ketone, what are we going to get? You're going to get that plus water. Okay? If you want to sit down and do this mechanistically, go all the way through it, you can get your product. There's also a little bit of memorization here, okay? Aldehydes, ketones, alcohols, acetal. Okay? This is an acetal. It's just we kind of focused on the diol. We brought in the aldehyde or ketone. That carbon used to be aldehyde or ketone. The carbonyl oxygen is lost, and instead the two oxygens are now bonded to the carbon. So it's a cyclic acetal. But now you can react this with magnesium, and you can get your Grignard, because this is no longer acidic over here. You no longer have the acidic protons. You can make your Grignard, you can react with the whatever you want, and at the very end, you can then come back and liberate your diol by reacting this with what? How do you go from acetal back to
Water.
lots of water and acid, drive it the other way? So H3O plus. You liberate the two alcohols and the carbonyl compound. Just as an aside, this is an acetal that came from acetone. Acetals that come from acetone are called acetonide. Acetonides. And if you look at the other handout, triamcinolone, it's used for like skin conditions. It's a steroidal compound. It's got the steroid nucleus. You see this diol here. Of course, it's got another OH. It's got two other OHs. But this down here is triamcinolone acetonide. That's because here the diol is converted to an acetal. And you see the acetone that used to be there? Cleave this back, you'll get the diol plus what? Plus acetone. You've got to be able to see that. Okay? There's some other questions there. One of these is given orally, and one of these is used as a topical, like an ointment or cream. It's two very different formulations. Okay? You want to take something orally, you tend to want to think about water solubility, because the stomach is water-based. If you wanted to get it in a cream or an ointment, those are more oily. Okay? So if you want to dissolve in that oil, well, you don't want it to be so polar. Okay? So take a look at that. Structures of some sugars. Acetals as drugs, we just saw one there. There's a few times you see acetals as drugs. They can decompose back to the carbonyl compound, but sometimes it's not too fast. Let's look at the sugars real quick. In the white handout, this page here, your carbohydrates, also known as sugars, from sucrose. Sucrose is a disaccharide, right? Saccharides, carbohydrates, it all refers to the same thing. Here's an open chain, this is glucose, it's a monosaccharide, open chain form. Okay, but it has many functional groups, and those functional groups can come together and make a ring. What comes together? Here's your aldehyde, which is here. 1, 2, 3, 4, 5. 5 carbons away, the OH. 1, 2, 3, 4, 5. Now you see this little typo here? What's missing there? An OH. They also left it off over here, the H off over there, and I wrote it in. But turns out that this OH actually adds to the carbonyl to make the ring. And you get a 6-membered ring, 5 carbons and 1 oxygen. And this is showing it in here. This could be catalyzed by acid. You could protonate this first, or you can just do it neutral form. Then you transfer the proton to the oxygen. So over here, and you get your ring form. This is called the open chain form. This is called the pyranose form. It's a 6-membered ring. And your monosaccharides are in equilibrium between open chain form and ring form. Okay? Now your ring form, the OH here, they've shown it generic here, and they didn't even put the H on there. The OH can be equatorial or axial. They're trying to show it generic, like it's your choice. Or we can say up or down. Now if the OH is down, that's called the anomeric form. I'm sorry, not the anomeric form, the alpha form. Yeah, this is shown below, I think. If the OH is up or equatorial, it's called the beta form. This is shown just in a different, this is just a repeat of what's above, basically. It's showing the cyclization. It can cyclize to the alpha form, or it can cyclize to the beta form. Now, which is going to be favored? That new OH being axial or equatorial? Equatorial is your first thought, unless something is making it want to go axial. But actually, the axial is favored. Your beta is your favorite form with glucose. But you can take a look at that. Important to point out here, though, is, and we'll look at this down here where it's not so generic. What functional group is this right here? There's a carbon. What's it got on it? An OR and an OH. What's that? Hemiacetal. Half acetal. If it was a carbon with 2 ORs, it'd be an acetal. If it was a carbon with 2 OHs, it'd be a well, you call it diol, but also known as a hydrate. Yes. So it's in between hydrate and acetal. It's a hemiacetal. Okay? The cyclic form of your carbohydrates are hemiacetals. All right, take a look at that. Pretty sweet, huh? So we'll see carbohydrates in biochemistry. Okay, so whenever you look at this stuff, you got to think 30,000 feet view, narrow down to, okay, exactly. So what did we just do in a 30,000 foot view? We reacted aldehydes and ketones with alcohols. Okay, that's what we just did. Initially, you get a half acetal, then you eliminate the water and you get your acetal. Now let's react aldehydes and ketones with amines. For example, this ketone reacting with ammonia, you can use an acid catalyst, you get an imine. We've seen these in lab, right? Everybody made an imine. Plus water. Carbonyl oxygen is lost as water. Imine. This is our first look at imine other than lab. Not amine, or just amine, but it's spelled with an I. A lot of times when somebody says, I'm going to make an amine or imine? Okay. Now, imines are also known as what? Shift bases. Right? As mentioned in the lab manual. Shift bases. That's what they're called in biochemistry. Biochemistry call them biochemists call them shift bases. Because the nitrogen is slightly basic. The lone pairs in a hydrogen, it's sp2, but it is slightly basic. Similar basicity is like pyridine. Okay? And your body uses imines as bases a good bit. Where your oxygen lone pairs, while it's similar hybridization, or the same hybridization, because oxygen is just more greedy, holds its electrons tighter, it's a better parent, your oxygen lone pair is just not considered basic. Of course, you can protonate this, right? We can protonate that with a strong acid. But it's just not basic enough to go do work as a base. That's just like the difference between water and ammonia. I mean, water is just not considered that basic, but ammonia is considered basic. Okay, so amines have some basicity known as shift bases. This is ammonia. You know, 100 years ago, they used to show mechanisms like this. They would have NH, and then they'd have two over here. They'd circle this, and they'd circle that, and they'd say, hey, you get water. Okay, and one H is left here. Okay? And that was about all the mechanism you would ever see. All right? But in terms of just balancing your reaction, you know, the oxygen is lost, but you also lose two H's from here. That's how you get water. One H remains. All right? Now here, if you lose two H's and O to make water, how many H's left on the nitrogen? None, just the methyl group. And you're not going to lose the methyl typically if you can lose an H. And usually you're not going to lose a methyl at all, although there's some unique mechanisms where you can dealkylate. So let's do the mechanism for this second one with the primary amine. Well, what you want to do first? Well, if we're using an acid catalyst, which implies strong acid, what's the first thing you want to do here? Protonate, right? And so we can get boom, boom, boom. This makes the carbonyl more electrophilic. That oxygen now wants the electrons, and these can be, you can even move these up and show a resonance structure. Or we can just bring in the nucleophile and do nucleophilic addition. Give that oxygen what it wants. And now nitrogen's bonded there, and there's two H's, and there's a methyl. And that's a plus charge. Now, unfortunately, on quizzes and tests, at this point, I'll usually see H's just have disappeared, and no charge, et cetera, et cetera. Okay? So, very basic here, right? I don't know what to say other than you got to see what's going on. We just made a bond, nitrogen made a bond to carbon, that's what this arrow means. We've not lost any H's or methyls. And of course, this nitrogen is a plus charge. We learned that at week 1 of organic 1. Okay. Well, ultimately, we're going to get rid of that oxygen. So what do you want to do next? like H3O plus. This is something with a plus. It can lose an H. It's going to be relatively acidic. We can do proton transfer. And we can get to boom, 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 boom. We can put the H on the oxygen. Now, I've never used an mechanism arrow for this because it's probably two different molecules. The OH of one molecule taking the H from this one. And everything's in equilibrium here. As a by the way, which one's favored? Which structure would you say is more favored, right or left? Would you rather have proton on nitrogen or oxygen? Nitrogen's more basic. This is probably more favored. Isn't like ammonia more basic than water?
Yeah.
Okay. So the equilibrium may lie like more towards this. This is not that bad. It's not like we're making a minus and a plus. What do you want to do next? Anytime you make a double bond, a pi bond using a lone pair, kick off a leaving group. We made that a better leaving group by taking advantage of the proton. We do have an acid catalyst, so you might as well use it. That would give boom, boom, boom. I'm going to move my methyl up so I can make the double bond to N. It's got a methyl and an H. That's a plus charge, by the way. Plus what? Plus water. There's your water. What do we need to do to get final product? Yeah, something needs to take it. This could have been maybe a little HCl that we use or something. And this can take the H, leave electrons behind. Okay. Many of you are not showing your bonds out on quizzes and tests and are not including this second arrow here. A lot of you are just doing this and just doing something like this. It's preferable to show this bond drawn out. We tack the H and then saying, hey, these two electrons move on to the nitrogen as what? As a lone pair. Okay? And that's what, there's a lone pair there. Many of you are also doing this and not being that precise. Here and then doing something like this. This looks like the H is moving on to the nitrogen. So a little more precision and say, hey, the electrons are moving on to the nitrogen. The chlorine is bonding to the H. So just a little more precision there. There you go. Anything really new there or odd or crazy? This is equilibrium. Can it be reversed? Sure, we're under Roman numeral 2. You drive it to the right by removing water. How do you come back to the aldehyde ketone plus the amine? Yes. And in this mechanism, an acid catalyst. If you had the imine, could you protonate it and get this? And if you protonate it, could water add here and give the electrons to nitrogen? This is like a protonated carbonyl. If under my hand was oxygen, that'd be a protonated carbonyl. So water can add. If water added, you give the electrons to nitrogen, you get to this. Move the proton to nitrogen to get that? Sure. Now, could you move these in and kick off the nitrogen? Yeah, and then you take the H back. So all that's reversible. I already know the question. Tell it to me, Larry.
In the lab, there's no acid catalyst.
Yeah, and there's another point to it, too. We didn't have to drive it. Yeah. Yes. You don't actually need, well, hold on. Traditionally, you do use an acid catalyst. There's two things to say here. First off, you can never have your cake and eat it too. Okay? We have a problem here. Ammonia is a base. If you throw in H plus, what's ammonia going to do with the H plus? It'll protonate it. You can't use too much acid catalyst or it really won't work. Because if you add too much acid, you'll just protonate all of your amine, and then there's no nucleophile. So a lot of books will talk about the exact amount of catalyst in the exact pH range. So you want to use a very small amount of catalyst. Because you're dealing with a basic reagent. All right? Now, everything's in equilibrium and it'll work out. But if you use too much acid, you'll just slow it down, really. You also don't really often need an acid because ammonia is a pretty darn good nucleophile. And so you don't have to really protonate the carbonyl. Although most mechanisms you see in textbooks will do it. You could do this without the proton. You would just take a proton off every species. That is, you would just attack without protonating it. That would actually be minus. Then you would transfer this to go neutral. Then you would move in and you would kick off hydroxide. That's okay, because anytime you make a pi bond, kick off a leaving group, it's easy to do. Yeah, when you hydrolyze, well, if you hydrolyze an amide, you kick off a nitrogen anion under basic conditions. Okay? Yeah. You can move this in and kick off hydroxide. And this, anytime you make a pi bond, kick off a leaving group. What we said is, if you've ever seen it minus, you can kick it off. Have you ever seen hydroxide minus? All the time. Okay? We're not doing SN1, SN2. All right? So that's one thing. So you don't always need the acid catalyst. This is one case. Typically, most all reactions we do that are acid catalyzed, you need the acid catalyst. This one you don't. But still, there's kind of exceptions. The reason we don't really need it in the lab we did, and we didn't have to drive it, is because the imine we made was so conjugated. Okay? See, there's no conjugation of the double bond here. This here you'd have to drive. But if you, let me make you another imine. If you make an imine, boom, 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 here, and then let's maybe put something like this. Well, instead of a double bond, we'll still make double bond, but let's turn it into an aromatic ring. Still double bond, and maybe let's make this an aromatic ring. And you could maybe make this an aromatic ring. Okay? Now look at all this conjugation here. I mean, it's all the way through. All this conjugation here, that's kind of cross-conjugated. All those pi bonds conjugated is going to make this very stable and this very, very favored. And if you can stabilize this somehow, for example, by lots of conjugation, it'll drive the equilibrium that way towards that product. And you don't have to worry about driving it some other way by removing the water. And that's what was going on in the lab. Because if you look at your imine you made in lab, it's very conjugated. Where a lot of times, usually like the one shown, you'd have to drive it by removing the water. So, the one you made in lab was sort of unique. Other questions about that? I think there's one other thing that drives it in lab. That is, if you remember when you made the imine, it precipitated. Okay? So, how can you drive it to the right? Remove the water as it's formed. But you can also remove the imine. What's a way to remove the imine? If it precipitates, it's actually being removed from the equilibrium because it's no longer dissolved and in that equilibrium. So if something precipitates, the equilibrium that's dissolved and in solution will be driven to the right because the product is no longer there, in essence, because it has separated out. Aha! Makes sense, doesn't it? So there's a number of things going on there. Some good stuff, good practical stuff there. Okay, show products. Basically, a little bit of memorization, okay? That's okay, guys, but then your mechanistic knowledge has to kick in. Aldehydes, ketones, and amines, what's it going to give? And amines. What's the product? Imine. Okay, aldehyde, ketone, there you go. What is an imine, real quick? I didn't say it like this, but an imine is essentially, it's analogous to a carbonyl, except instead of an oxygen, it's a, it's a C double bond O, it's C double bond N. And since N takes one more bond, the nitrogen is going to have something bonded to it. Okay, so it's your carbonyl equivalent, but it's a nitrogen instead of an oxygen. Or you can say it's C double bond N, alkene equivalent with nitrogen instead of carbon. There you go. So you can use a little dismemorization here. You guys on the left show the product of the first, you guys on the right show the product of the second. Then we'll look at what you get if you use a secondary amine. I'm going to start with my aldehyde here. There's your aldehyde. Double bond. Instead of oxygen, it's double bonded to what now? Nitrogen. And the nitrogen has what? What do you call that group on the nitrogen? Benzyl. Benzyl, right? That's benzylamine. There you go. The nitrogen replaced the oxygen. What else did you form there in a balanced equation? Water. The oxygen got kicked off from the two H's from the nitrogen. Okay? A little bit of memorization there, but then your mechanistic knowledge, okay, how that actually happens. Down here. And what's on the nitrogen? Propyl. Okay. Are those bonded together right there?
Yeah.
Okay. Yeah, that's a 6-member group. Can you have isomers with either of these? Are these isomers or are these the same compound?
No, they're isomers. The double bond, the metal are on their different sides or on the same.
These are like cis-trans-alkene isomers. Here, the benzyl and the methyl are on the same side. Here, the benzyl and the methyl are on opposite sides. Okay? That's a pi bond there that lacks rotation. That's just like your alkene cis-trans. Okay? Imines can have, what type of isomers are those? They're not constitutional. It's stereoisomers, right? There's two types of stereoisomers, right? What are the two types? Diastereomers and enantiomers. What are those two up there? No, the mirror image of cis is what? Mirror image of cis is cis. Stand in the mirror and hold your arms like this. Your mirror image will also be cis. If your mirror image is doing this, let me know. Okay? Those are like cis-trans. Cis-trans are diastereomers. Those are diastereomers. You can call them cis or trans, or you can say E or Z. But it's analogous to alkenes, okay? Can this one, does this one have a diastereomer? No, because it's symmetrical there, okay? Now in the lab, the imine often gave 2 spots on TLC. I think it's because you're getting cis and trans diastereomers. Okay? The one you made in lab, even after recrystallization. Now this week we're doing Wittig, and the Wittig is making an alkene, and you can also have cis-trans. Now usually when you make the Wittig, when you recrystallize, usually you only get 1 diastereomer, and your TLC shows only 1 spot. But before you recrystallize, you will see 2 spots, and that will be the cis-trans diastereomer of your alkene. Okay, so imines can have cis-trans, but not the one on the bottom. What if you react an aldehyde ketone with a secondary amine? Let's see. Oxygen here, lose 2 H's to make water. Oh, wait a minute. This only has 1 H to lose. Where's the other H come from? Then you're saying it's not reformed? Because unless you regenerate H+, you can't call it a catalyst.
The carbon. It's not the carbon.
If you look at this, 2 H's here, now there's only 1 there. Another H has to come from a carbon. We'll do the mechanism, okay? But this is not an imine. This is one of my favorite functions here. Enamine. Why is it ene? Alkene. It's an alkene with an amine. And it's enamine. All right? How do you get to enamine? Well, let's do mechanism. Let's protonate this. Okay, we know how to do that. Nitrogen adds, electrons up. Let's get to the point where in H, 2 methyls, right? There's 2 methyls plus charge. Proton transfer. Two methyls remaining. Now anytime you can make a pi bond, kick off a leaving group. Easy to do, especially if it's protonated like this. That's going to give boom, 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 boom. Double bond to N, methyl, methyl plus charge, plus water, right? Okay? Remember before when we did the mechanism, the last step was to lose a final H here and to go neutral. That doesn't have another H to lose. Instead, we're going to lose one of these over here. Now you can do this different ways. We could just take the H here, move the electrons in. I'm going to do it by doing a resonance structure. Okay. Nitrogen's electronegative. It wants these electrons. We can just move them over, right? That would be just doing resonance. And if we move them over, we get boom, boom, methyl, methyl, boom, boom, boom. What's now here? Boom, boom. Yes, positive charge. Double-headed resonance. Okay? Now, we used maybe sulfuric acid, so we got an HSO4 minus here. We got to essentially lose an H and reform our catalyst. Well, now, we can take one of these and just move the electrons in. And that would give our final product, and we would reform our like sulfuric acid. What does that look like? That looks like the last step of a E1 elimination. I mean, you can eliminate this alcohol, right, and make the double bond. Acid catalyst, you can protonate, right? Then you can ionize, right? And then how do you put the double bond in? Then something takes the H, put the double bond in. That's your good old E1 elimination, right? Ionization being the fast step, the slow step, and then taking the beta hydrogen here, the fast step. So taking the H, putting the double bond in, okay? So, that's the only way you can lose that other H. And you actually get enamine. Nitrogen can't make, it's not going to be neutral with 4 bonds. So enamine. Questions about enamine? The functional group, not the wrapper. Everybody see it? Just a little twist at the end. Just need to sit down and go through the mechanism. Enamine. Now, if you use a tertiary amine, tertiary amines don't give lots of different functional groups. You're not going to get anything. You occasionally see enamines in drugs. For example, there's a drug used for fibromyalgia. I don't know how to pronounce it. Milnacipran, maybe? But what do you see right here? An alkene with a nitrogen. It's an enamine. Okay? And then you got this regular amine, or this primary amine. Nice cyclopropyl. Lots of drugs have cyclopropyl, more than you would expect. So a new functional group. Okay, imines. Imines are very versatile, and you see imines a good bit. There's also lots of specialized imines. A couple of specialized imines are here. Hydrozones and oximes. They're just special types of imines. If aldehyde or ketone, if you use hydrazine as the amine, this is called hydrazine, where you have 2 nitrogens bonded to each other. One of them is going to react. Okay? Now, I'm not showing an acid catalyst here. Again, you don't always need an acid catalyst. And you don't need it for here, especially. But if this reacts and you lose H2O, nitrogen, okay, there's your imine. But if the imine nitrogen is bonded to another nitrogen, that means you used a hydrazine to make the imine. This is called a hydrazone. Whenever you use a hydrazine to make it. There.
If I had 2 equivalents of the reagent there, would I end up with a...
Imine on both nitrogen?
Yeah.
It seems like probably you would. You just don't see those often. I don't know why. Probably though. There's lots of chemistry where both do react, especially to make rings. So, hydrazone. Typically you don't need an acid catalyst because, well, pretend like that's not a pi bond there. Because you have conjugation here. The lone pair being conjugated with the double bond usually is enough to drive it to the right. So you often don't need acid catalyst. Now, if you use hydroxylamine, which is NH2OH, It's a very common molecule, hydroxylamine. The nitrogen will make the imine. You'll just have on the nitrogen an OH. This type of imine is called an oxime. You may think it would be like a hydroxime or something, something. It's just known as an oxime. It's actually just a special type of imine. Mechanism is the same as before. But your hydrozones and your oximes are very common. And we'll finish up today. The Wolff-Kishner. We'll be looking at the Wolff-Kishner. Did we introduce the Wolff-Kishner during aromatic chemistry?
Yeah.
And we said later on we'll be looking at the mechanism? Well, later on is here. Before then, though, we do have a chemical test. If you take this hydrazine here, it's got something on the other nitrogen, aldehyde ketone. You get this hydrazine with the other nitrogen here. It's called a 2,4-dinitrophenylhydrazine. We'll pick up here tomorrow or Wednesday. Please be looking ahead, guys. Got lots to cover here. I'll be sending you another handout by email. No.